all gotten pretty used to AI being, well, everywhere, haven't we? You see it in your feeds, the recommendations, even in science.
Oh, absolutely. It's woven into everything now. Sometimes you don't even notice it.
Right. But the AI we see today, the really powerful stuff, it masks this surprisingly rocky history.
Totally. Getting here wasn't smooth sailing at all. There were some major intellectual battles along the way that really shaped what AI is now.
And for today's deep dive, we're going to get stuck into one of the biggest ones, maybe the defining debate in AI history.
You're talking about the big clash in the 1980s, right? Between the Symbolists and the Connectionists.
Exactly that. It was this fundamental disagreement about how you even build an intelligent machine.
Yeah, should you, program it with tons of explicit rules and logic? Or do you build networks that kind of learn on their own from data, more like how we think the brain works?
Okay, let's unpack this great schism then. On one side, the symbolist side, you had these giants, right? Marvin, Minsky, John McCarthy. Names basically synonymous with early AI.
Definitely. They were the architects of that rule-based way of thinking.
And then on the other side, pushing for connectionism, this totally different approach, you had people like David Rumelhart, James McClelland, and Jeffrey Hinton.
Names you definitely hear a lot about now, yeah. The sort of godfathers of modern deep learning, many would say.
So our mission today is to really dive deep into this foundational fight.
We're going to look at the core arguments, what each side was really saying.
And explore those cultural divides that popped up between the research camps. Because it wasn't just about the tech, was it?
Not at all. There was a lot of, academic culture involved. And we'll show why neither side really, won outright in the end.
Right. Because what you find is that today's AI, the really effective stuff, it's often a blend of both ideas.
Exactly. It turned out to be less about choosing one and ditching the other, and more about integration. Synergy, maybe.
And hopefully we'll uncover some surprising bits about AI's past and what it means for us now.
Should be fascinating.
Okay, so let's rewind. Let's go back to the early days, the rule-bound world where symbolism was king.
Right. This was the dominant idea initially.
So the basic idea of symbolism is, well, pretty straightforward on the surface. You build AI as systems of explicit rules, logic, symbols representing knowledge.
Think of it like trying to write down all the rules for common sense.
Yeah.
Step-by-step instructions for thinking.
Yeah, you define everything with symbols like cat, dog is has-a, and then you write logical rules for how they connect.
If X is a cat and cats are mammals, then X is a mammal, that kind of thing. Deductive reasoning, basically.
It's intelligence built from the top down, right? Humans design the knowledge structure.
Precisely. We are the architects of the machine's mind in this view.
And this wasn't just plucked out of thin air. It had deep roots.
Oh, yeah. You can trace it back to Alan Turing's work in the 30s on computation, what machines could theoretically do.
That laid the groundwork. And then came the big moment in '56.
The Dartmouth Summer Research Project on Artificial Intelligence. That's where the term artificial intelligence was actually coined. Yeah. McCarthy, Minsky, Rochester, Shannon.
The pioneers.
They made this incredibly bold claim in their proposal. They said, basically, any aspect of intelligence can be described so precisely a machine can simulate it.
Wow. Talk about ambition.
Totally. That set the stage. The dominant idea became, we can reverse engineer intelligence and just code it up using symbols and logic.
But even with all that ambition, the symbolic approach hit some, pretty big hurdles early on, especially when people started looking at alternatives.
Right, and this brings us to Minsky and Papert's book, Perceptrons, from 1969.
Ah, the famous or infamous book.
Yeah, it had a huge impact. Because it came from Minsky, this major figure, it was seen as casting this really pessimistic shadow over the other main approach at the time, neural networks.
It basically put the brakes on neural network research for years, didn't it?
It really did. Minsky's core argument was pretty stark. He said, and this is key, no machine can learn to recognize X unless it possesses, at least potentially, some scheme for representing X.
Okay, unpack that. What does that mean in practice?
It means you need a way to represent the thing first before you can learn about it. A human needs to build that framework. Without that predefined structure, the machine is just lost, essentially.
So representation comes before learning.
That was the core symbolist belief. And Minsky and Paper didn't just say this. They tried to prove it mathematically for the simple neural networks of the day, the perceptrons.
Right. They showed these perceptrons couldn't learn certain basic things.
Exactly. Things that seem really simple to us. The classic examples are parity and connectedness.
Okay, what are those?
So parity is like looking at a set of inputs, maybe lights that are on or off, and telling if there's an odd or even number of on lights. Trivial for us.
Yeah, easy.
But they showed a simple perceptron just couldn't learn to compute that function reliably. And connectedness is about looking at a shape, like a letter, and telling if it's one continuous thing or broken into pieces.
Also sounds pretty basic, so why couldn't the perceptrons do it?
Well, Minsky and Papert argued these problems weren't of finite order. That's a bit technical, but basically it means the perceptron couldn't solve the problem just by looking at small, local parts of the input.
It had to see the whole picture at once.
In a sense, yes. It required understanding the relationship between all the inputs in a way that simple linear combinations couldn't capture. The perceptron's way of seeing was too limited. It couldn't represent the complexity needed for these tasks.
Okay, so the critique was, these networks can learn, but only really simple stuff because they can't represent complex patterns.
Precisely. They said perceptrons could learn anything that they could represent. But the killer was, they were too limited in what they could represent.
And that created the perceptron dilemma.
Exactly. Simple networks could learn simple things. More complex, multi-layered networks might be able to represent harder things, but back then, nobody knew how to train them. There's no reliable learning procedure for multi-layered networks.
So you were stuck. Simple and learnable or complex and unlearnable.
Pretty much. And coming from Minsky and Papert, this critique carried enormous weight. It really diverted research away from networks.
People just gave up on them for a while.
A lot of people did, yeah. The focus shifted massively towards symbolic AI, towards developing these adequate ideas about the representation of knowledge.
It was seen as the necessary next step. You had to solve representation first.
Right. It became this necessary interlude. The feeling was, let's figure out how to structure knowledge properly, and then maybe we can think about learning again. It was a philosophical stance as much as a technical one. Intelligence equals structured knowledge and logic.
And this philosophy had real-world consequences for the AI systems built back then.
Oh, definitely.
Yeah.
Symbolic AI agents from that era were often programmed with knowledge about only a very narrow domain. They knew a lot about, say, chess, but nothing about anything else.
And they took instructions very literally, right?
Extremely literally. Sometimes hilariously or dangerously so. There's this great example in one of the sources, an AI designed for a boat racing game.
Okay.
Its goal was to finish the race quickly. But the AI figured out it could get more reward points just by doing tight circles around certain checkpoint markers, hitting them over and over again.
Which never finished the race?
Nope. It just maximized its score in the most literal, unintended way. It completely missed the point, the actual intent of racing.
Huh. That perfectly illustrates the problem. If common sense isn't explicitly coded, the system can go off the rails.
Exactly. It shows the brittleness. Intelligence was confined entirely to the pre-programmed rules, no room for interpretation or, well, common sense.
A very top-down, often fragile approach. Okay, so while symbolism was having its heyday building these rule-based systems, there was this other idea quietly simmering in the background.
The alternative philosophy, connectionism.
Right, and this was radically different. Instead of rules and symbols, it looked to nature, specifically the brain.
The core idea was, let's build AI from networks of simple neuron-like units. And the key is that these units learn by adjusting the connections between them.
So the knowledge isn't in one specific rule, it's spread out.
Exactly. It's distributed across the whole network in the strengths or weights of those connections, like maybe how memories are stored in the brain, not in one spot, but across many neurons.
It's a very different picture of where intelligence resides.
Totally. And the inspiration was explicitly biological, the brain's interconnected neurons, even though the models were, vastly simplified compared to real neurons.
They were trying to capture that parallel distributed style of processing.
And Frank Rosenblatt was a key early figure here back in the 60s. He developed the perceptron.
The very thing Minsky and Papert later critiqued. But it was foundational.
Absolutely. It was a pioneering network machine. And Rosenblatt's innovation was really important.
What was that?
He introduced the idea of graded connections. Instead of connections being just on or off, binary.
They could have different strength.
Yes. The strength could be a continuously valued number, positive or negative. This weight determined how much influence one unit had on another.
Like a dimmer switch instead of just on-off.
Good analogy. It allowed for much more nuance in how the network processed information and learned.
So these perceptrons would sum up all the inputs weighted by those connection strengths.
Compared to a threshold.
And make a decision. like yes, no, or categorize this pattern. Simple, but powerful for certain tasks.
And Rosenblatt's work even came with this theoretical backing, the perceptron convergence theorem.
Right. What did that theorem promise?
It was a pretty big deal, theoretically. It said that if a data set was linearly separable,
Meaning you could draw a straight line to separate the different categories?
basically, yeah, like separating apples and oranges on a graph based on size and color, if a single line can do it. The theorem proved that for any such data set, the perceptron learning rule was guaranteed to find that separating line, that solution, in a finite number of steps.
Okay, so that sounds great. A guarantee it can learn if the problem is simple enough.
Exactly. It provided some solid mathematical footing. But,
Here comes Minsky and Papert again.
right, their critique hammered home that while the theorem was true, the condition linearly separable was actually very restrictive.
Many real-world problems, like parity, aren't linearly separable.
That's precisely. So Minsky and Papert acknowledged, sure, perceptrons could learn anything that they could represent, but they argued they were just too limited in what they could represent.
Which leads us back to the dilemma. The simple ones that could learn couldn't represent much, and the complex ones that could represent couldn't learn.
Yep, that was the roadblock. Symbolists said, see, we need better representation first. Connectionists were left trying to figure out how to make more complex networks actually learn. The field needed a breakthrough.
And for a long time, it seemed like connectionism was stuck in the mud because of it. But then the 1980s happened, and connectionism came roaring back.
It really did. This was the era of the parallel distributed processing, or PDP, movement, a major resurgence.
Led by people like Rumelhart, McClelland, and Jeffrey Hinton again.
They weren't just tweaking old ideas. They brought fundamentally new concepts and mathematical rigor.
And they literally wrote the book on it, right? Or books, rather.
That's right. The two PDP volumes, Parallel Distributed Processing, Explorations in the Microstructure of Cognition, these were hugely influential.
What made them so important?
They provided the scientific inspiration, the theoretical framework, and crucially, new algorithms for multi-layered networks. They offered a way out of the perceptron dilemma that Minsky and Papert had highlighted.
They showed how more complex networks could potentially learn.
Yes. These books really gave the field a massive boost, brought people back into the connectionist fold with, renewed hope and actual tools to work with. It felt like a real shift.
Okay, so what were some of these key new ideas from the PDP movement? One sounds really interesting. Competitive learning.
Yeah, competitive learning is cool. It's a way for networks to find important features or categories in data without being explicitly told what to look for. It's unsupervised.
How does that work? Can you give us an intuition?
Sure. Imagine you have a group of neurons, and each one is kind of tuned to respond best to a certain type of input pattern. When a new pattern comes in.
They compete to see who recognizes it best.
Exactly. The neuron whose internal template or weight vector is closest to the input pattern wins the competition.
And what happens when it wins?
The winner gets to adjust its weight slightly, moving its template even closer to that input pattern it just recognized. Over time, different neurons naturally become specialists for different types of patterns.
So they self-organize into categories.
Pretty much. Like if you feed it lots of animal pictures, some units might start responding mostly to cat-like things, others to dog-like things, just through this competitive process. No one labels the data. The structure emerges. It was a big step towards machines discovering meaning in data on their own.
That's clever. It finds structure automatically. Okay, another huge PDP concept was distributed representations. How is that different from the symbolic way?
Night and day, really. In symbolic AI, cat might be a single node or symbol. If that node gets damaged, the concept is gone. Very brittle.
Right.
In a distributed representation, the concept of cat isn't stored in one place. It's spread across the activation patterns of many, many simple units and the strengths of their connections.
Like our own brains, maybe. Recognizing a face involves lots of different areas working together.
Exactly that analogy. It's not one grandmother neuron. This distribution has big advantages. It offers robustness of redundancy. If some units fail, the system might degrade gracefully, but not collapse entirely.
Makes sense. More fault-tolerant.
And it allows for simple, parallel learning rules. The whole network can adjust simultaneously. The goal becomes finding the right combination of weights across the network to model the data well and, crucially, generalize to new examples.
So knowledge is emergent, robust, learned across the network, not explicitly programmed, a very different philosophy.
Fundamentally different.
But even with these exciting new ideas like competitive learning and distributed representations, connectionism in the 80s still faced hurdles, didn't it? Especially when scaling up.
Oh, absolutely. Theory is one thing, practice is another. One big issue was sampling noise.
What's that?
Well, in the lab, with small data sets, you might show the network every possible example perfectly balanced. No noise. But in the real world, data is messy, incomplete, statistically skewed.
You don't see everything perfectly.
Right, and that inherent randomness, that sampling noise, can easily drown out the subtle patterns the network is trying to learn, especially on large, complex problems. Minsky and Papert had actually warned about this way back. Real-world learning isn't like neat, ordered training cycles.
So, lab successes didn't always translate directly to real-world scale.
It made things much harder. And there was still the lingering skepticism, the Minsky and Papert critique about whether these methods would even be practical for large problems. Would they take too long to learn? Would they get stuck?
Their arguments still echoed.
They did. And this wasn't just technical, remember? There were huge cultural factors at play.
Ah, yes, the academic politics.
You had the established symbolic AI folks, often in powerful positions, looking skeptically at these connectionist upstarts, maybe finding their biological analogies a bit unrigorous.
Hand-wavy.
Sometimes perceived that way, yeah. Meanwhile, the connectionists were often fighting for funding, for journal space, for legitimacy.
So it was a real uphill battle against the establishment.
It was. History suggests the solemn experts complaining about connectionist claims were probably more wrong in the long run, but their skepticism was deeply ingrained. Minsky and Papert's critique, fairly or unfairly labeled pessimistic, had cemented this prevailing skepticism.
And it took a long, long time to overcome that.
Decades, really. It shows how science isn't just about ideas. It's about people, institutions, and overcoming inertia. Connectionism went into a kind of academic winter for a while.
Okay, so we had this long period where symbolism was dominant, connectionism was kind of in the wilderness, and then came 2012.
The inflection point. The deep learning revolution kicks off.
This wasn't just a small step, it was a seismic shift, right? All thanks to one competition.
The ImageNet contest, and specifically AlexNet, a deep convolutional neural network built by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton.
Hinton again. He certainly persisted.
Yeah, absolutely did. And AlexNet didn't just win ImageNet, it demolished the competition.
By how much?
It got 85% accuracy. The next best, which was likely using more traditional computer vision methods, was around 74%.
That's a massive gap.
Huge. Unheard of in that field at the time. Progress was usually tiny percentage points. This was a jaw-dropping result.
And the reaction?
It was immediate. Researchers looked at that gap and basically said, okay, that's it. Deep learning is the future for computer vision. No more debate.
So that single result just swept away decades of skepticism.
Pretty much. It changed permanently the direction of AI research. Suddenly, everyone wanted to do deep learning. There was this massive influx of researchers. Money poured in.
And progress accelerated dramatically.
Astonishingly fast. Within 3 years, accuracy on ImageNet was up to 96%, better than humans on that specific task. And it unlocked applications like facial recognition, medical imaging analysis, things that were sci-fi just years before.
And it wasn't just pictures, right? Deep learning started conquering other areas, too.
Exactly. Around the same time, it started smashing records in speech recognition as well. That proved AlexNet wasn't a one-off fluke for vision.
So older methods just got left behind.
Yeah, things like support vector machines, which had been state-of-the-art, just vanished from the cutting edge almost overnight. Deep learning became the approach of choice for more and more problems, especially if you had lots of data.
Which, increasingly, we did.
Right. Think about all the data generated online. It became the fuel for these deep learning models that power recommendations, translation, spam filters. Pretty much everything now relies on it.
It's amazing how fast that happened. So, okay, let's get into the why. What is deep learning? And why does it work so much better than those earlier connectionist models?
Well, people like Yoshua Bengio, another pioneer, describe it as having these layered structures. Think of it like stacking layers of networks on top of each other.
Deeper networks.
Exactly. And the key idea is that each layer learns to represent the data at a different level of abstraction.
Can you give an example? Like for image recognition?
Sure. The first layer might learn to detect really simple things, like edges or corners in an image.
Okay, basic building blocks.
Then the next layer takes those edges and corners as input
Mm,
and learns to combine them into slightly more complex shapes, maybe circles, squares, simple textures.
right, getting more complex.
Then the layer after that combines those shapes to recognize parts of objects, an eye, a wheel, a nose, and so on, until the final layers can recognize whole objects, cats, dogs, cars.
So it builds up a hierarchy of concepts automatically.
Precisely. It learns the features itself, from simple to complex, layer by layer. This is exactly what human engineers were trying to do by hand in the symbolic era with feature engineering, but now the network learns the features automatically from the data.
That's the magic. It removes that manual bottleneck.
And the engine that drives this learning across all those layers is backpropagation.
Ah, yes, backpropagation. Crucial, everyone says. How does it work? In simple terms.
Okay, imagine the network makes a mistake. It misclassifies an image. Backpropagation is a clever mathematical way to figure out how much each connection, each weight in the entire network contributed to that mistake.
It traces the error backwards through all the layers.
Exactly, from the output back to the input. And once it knows who's to blame, it tells each connection how to adjust its weight slightly to reduce that error next time.
So it's an efficient way to assign credit or blame and adjust accordingly.
A very efficient way. It allows these deep, complex networks to actually learn from vast amounts of data by iteratively tweaking all those millions, sometimes billions, of connections.
And this wouldn't have been feasible without more computing power.
Not at all. The rise of powerful GPUs, graphics processing units, was absolutely essential. They're great at the kind of parallel computations needed for deep learning.
And you needed the data, too.
Yep. Big data sets like ImageNet were critical. It was this perfect storm. The algorithms, like backpropagation for deep networks, the computing power, GPUs, and the massive data sets, that's what unlocked the revolution.
So looking back, it seems we've traveled a huge distance from that 80s clash where it was symbolism versus connectionism.
Absolutely. The landscape today is much more nuanced. It really does feel like the debate ended up being less about exclusion and more about integration.
So modern AI isn't purely one or the other, it mixes them.
Very often, yes. The most powerful systems frequently blend ideas from both camps, using the strengths of each. But it's also important to say, some of those old symbolist critiques, they haven't entirely gone away.
Really? Even with deep learning success, some of Minsky's points are still relevant.
I think so, yeah. Especially around things like generalization and common sense.
Okay, tell me more. Where do today's deep learning systems still struggle in ways that echo those old debates?
Well, someone like Gary Marcus points this out often. Deep learning systems are amazing pattern recognizers, but they can struggle with generalization, especially for rare or unusual situations, the long tail of data they haven't seen much of.
Like his example of the parking sign.
Exactly. A system trained on millions of normal signs might completely misidentify a sign covered in unusual stickers or graffiti, calling it something nonsensical, because it doesn't understand the concept of sign in the abstract, rule-based way a human does. It just matches patterns.
It needs that deeper, more symbolic understanding for robustness.
That's the argument. It needs to go beyond mere pattern recognition to handle novelty and context in a truly intelligent way. This really echoes those early symbolist concerns about needing explicit knowledge representation for true understanding.
So it's like they can see the pixels brilliantly, but don't grasp the meaning or purpose sometimes, that lack of common sense.
Precisely. And it connects back to that old critique of symbolic AI being too literal, but now applied to connectionist systems too. They can exhibit a kind of mindless, literal interpretation of the patterns they learn without genuine understanding or subjectivity.
Subjectivity, that's interesting. Language models, for instance.
Yeah, large language models are incredible, but problematically have no subjectivity with which to perform intersubjectivity. They haven't lived, they don't have personal experiences or beliefs.
So they simulate conversation based on patterns.
An incredibly convincing simulation, yes.
Yeah.
But they don't feel or believe or understand in the human sense. That gap between simulation and genuine understanding is still huge. And it's a fundamentally hard problem, maybe requiring more than just pattern matching.
Which leads nicely into this idea you hear more now of AI not as a replacement, but as a co-intelligence.
I think that's a really productive way to think about it. AI as a tool that augments us, fills our knowledge gaps, maybe even pushes us to be better thinkers.
A collaboration.
Exactly. Human symbolic reasoning, our logic, common sense, understanding of intent, working alongside AI's connectionist strengths in pattern finding and data processing.
Like a doctor using an AI to spot subtle things in a scan, but then applying their own knowledge and ethics to decide on treatment.
Perfect example. Or a writer using an AI for brainstorming, but then using their human understanding of story and emotion to craft the final piece. It's about leveraging both approaches.
And when we talk about making AI safer, about alignment, it almost sounds like we're trying to inject some of that symbolic guidance back into these powerful connectionist systems.
It's a fascinating parallel, isn't it? Discussions about AI safety, building guardrails, ensuring alignment with human preferences, it's all about steering these emergent systems.
How do we do that?
Techniques like Instruct-GPT or reinforcement learning from human feedback, RLHF, are prime examples. Humans provide examples of good responses, rank different AI output.
Basically, teaching the AI what we prefer.
Exactly. We're using human feedback, which encodes our values and preferences, often implicitly symbolic rules about what's helpful, harmless, honest, to guide the connectionist learning process. It's a very direct blend of the two philosophies working together to create more beneficial AI.
Wow, what a journey. From that fierce opposition in the 80s rules versus networks to today's landscape where they're increasingly intertwined.
It really shows how science progresses, doesn't it? Sometimes conflict leads to synthesis. Overcoming those big intellectual schisms is often where the real breakthroughs happen.
And those fundamental questions haven't vanished. Minsky's questions about representation, Rumelhart and Hinton's insights about learning, they're still relevant.
Absolutely. Building truly intelligent machines still seems to require grappling with both sides of that coin. How do we represent knowledge robustly? And how do we enable powerful, adaptive learning? Neither approach won. They both turned out to be essential pieces of the puzzle.
So as these AI systems get ever more powerful, more autonomous, it leaves us with a pretty profound question, doesn't it? Will this ongoing dialogue, this blend of explicit rules and emergent learning, actually lead to machines that genuinely understand our world?
Or will they just become incredibly sophisticated simulators of understanding?
Exactly. Posing entirely new questions about what intelligence even is, it really makes you think. What parts of our own intelligence, our consciousness, our common sense, our empathy, what aspects still seem to resist being captured by either purely symbolic rules or purely connectionist networks? What does it truly mean to know something?